So I think we're going. We're going to give this a shot one more time with the optimization day 2. I'm doing it old school with the older course. It won't be all fancy, but it'll be spectacular nonetheless. So here we go with optimization day 2. And optimization day 2 starts where optimization day number 1 ended, and where also optimization day 1 began, which is the question where the maximums and minimums occur. The answer is maximums and minimums occur, say it with me, the critical numbers, right? That's where we have the max and mins. Okay, the critical numbers. And how do we find critical numbers? From the derivative, f prime of x is equal to 0. Okay, so maximums occur at the critical numbers. That's where the derivative equals 0. Of course, we look for that sign change when we're doing a curve, but that's the idea. Let's do some problems. So we've got a page. It's got 24 square inches of print. That's this part down in here, the gray and the dots in. Okay, it's got 1 inch margins on the left and the right, 1 inch there, 1 inch there. And it's got 1.5 inch margins on the top and the bottom. What we want to know is what's the minimum paper size that we can have that meets all these conditions. Okay, so we're going to have to make ourselves a little equation. What we know, let's see, we know a couple of things. We know they've got 24 square inches of print, and that's this part here, but we don't know how wide the print is, so we're going to call that x, nor do we know how tall the print is. So what we know is that the area of the print is 24, so we'll make a little equation, x times y is 24. That's kind of our backup equation that we're going to use. The primary equation that we're going to end up with is the width and length of the paper, the area of the paper. That's what we're trying to minimize, is the area of the paper, the minimum paper size. So if this is x and there's a 1 and a 1 and 1, this length right here is x plus 2. Make sense? And down top, y plus 3. So my area of my paper is just x plus 2 multiplied by y plus 3. And this is the thing we're going to want to take the derivative of, and this is the thing that we're going to find out when it's equal to 0. But we don't want to do this with x's and y's because we're going to implicit differentiation. What we can do is we can figure out what y is, and y is equal to 24 over x. So we'll back substitute that in there. Getting tired of the red. Maybe you are, maybe you aren't. The area is... Alright, so where was it? Oh yeah, I was telling you about the area. And so we're just going to rewrite this equation as x plus 2. And instead of y, we're going to write 24 over x plus 3. And then we're going to do our little multiplication dealio. Get it out of the way. So x times 24 over x is probably 24. I don't want to keep losing my thing. Inside we've got 48 over x. Let's see, outside is going to be 3x. And my last is going to be 6. So I want to find the derivative of that. So I will. And I could do 24 plus 6 is 30 and take the derivative, but I know they're both constants, so they're going to go away when I'm done here. So my derivative, a prime, is going to be what? Probably negative 48 over x squared. Stop and think if you're not sure. Plus 3. That's a 3. So we're going to look for when negative 48 over x squared plus 3 is equal to 0. And so what we're going to be looking for is, let's see, negative 48, I'm going just up here, over x squared plus 3 is equal to 0, or when 3 is equal to 48 over x squared, or when 3x squared is equal to 48, or when x squared is equal to 16, so x equals plus minus 4. Okay, and so since we're talking about the width of the paper, probably it's not going to be negative 4 because you can't have negative 4 inches of anything, so we're going to just look at the positive root, the x equals positive 4 as my possible root there. We should do a second derivative real quick, so this is supposed to say squared up here before anybody freaks out on me. And so when I do this one, second derivative turns out to be, let's see, a double primed is going to be positive 96, yeah, 96 over x cubed. So when x is 4, that's going to be positive. It's going to be greater than 0, which means that I'm concave up, which means that I have a max. Okay, using that second derivative test to check out that everything works. So to actually answer the question, what's the minimum paper size? So if x is 6, that means that y is 4. 6 times 4 is 24, right? And so my paper is 8 wide and 4 plus 3, 7 tall. So 8 by 7 inch paper gets the job done for me. Okay, so that's that problem. It's a problem for you. I want you to design a can that holds 500 milliliters with a minimum surface area. So a half-liter can with a minimum surface area, which would mean it would have less metal in it, which would save us money theoretically, right? So a couple things to help you out. One is that 500 milliliters is the same as 500 cubic centimeters. Okay. Also that the volume of a can, cylinder, pi r squared times h. We're going to assume it's just a perfect cylinder, not we're going to ignore the taper, we're going to ignore the inner part. So we're just trying to figure out the cylinder. Volume is pi r squared h. And surface area is, let's see, we've got the top and the bottom, so those are round, 2 pi r squared. And then we've got the side, which is 2 pi r h. 2 pi r is the circumference, h is the height, so that gets me the surface area. Okay? We're trying to minimize the surface area. That's the amount of metal that we're going to use. So you're going to need to find surface area prime. Okay. What we also know is that the volume is equal to 500. So we can take this equation and solve it for h, and then use that h for this h, simplify, and take the derivative and find the critical numbers, and then check it out. Okay. So I'd love you to find that answer out, and I'm not going to put it in this video. I'd love you to find out that answer. I'd love you to actually, when you get the dimensions, build the can. See whether you like it. See whether it's a can that people would make for a half-liter can of soda. And that's what I think you should do. Okay, so figure it out. Find out when the derivative is equal to 0. Figure out the radius. Figure out the height. Make the can. Just make it out of paper. Just take a piece of paper. You know, a strip of. Basically, you take a strip of paper like so. Make it round. You'll have the can. But of course, you need to know what the height is, and you'll need to know what the radius is, so you can figure out some stuff. So make that can. Okay. Let's see what else we got for you. So there's that. And that's about all. Okay. So max and mins, they occur at critical numbers. Critical numbers happen when the derivative equals 0. So we need to be able to find those as we go through our world. Okay. Hey, thanks for watching. Thanks for listening. Thanks for just about everything. We will see you very soon. Bye bye.